Hello, I'm Professor Tham Ratnaraja from University of Edinburgh. In this video, we are going to show our full duplex demo that we built in collaboration with Professor Madini's research group at Heriot Watt University. I am here at the Heriot Watt University's wireless technology lab. I'm going to show our demo here. As we all know, currently all the wireless systems are working in the half duplex mode. That means is the transmitter and receive at a different time, or it can happen in different frequency. The full duplex is the emerging concept where the transceiver is receiving and transmitting at the same time. This means theoretically we will double the spectral efficiency in the point-to-point system. Here in this demo, we are going to show the single cell scenario. This is the multi-user scenario here. There's a base station is equipped with the full duplex capability, and there's an uplink user communicating with the base station. Uplink user is operating in the half duplex mode, and there are two downlink users also operating in the half duplex mode as well. This is our full duplex single cell scenario here. This is base station. This is the transmit antenna, and this is the receive antenna of the base station. So in other words, the base station is equipped with two antenna, one for transmitting and one for receiving. And this is the uplink user communicating with the base station here, and these two are the downlink users. These two are the downlink users. One of them is the weak user. This one is the weak user. This is a strong user. In the downlink, we are using NOMA concept to communicating to the downlink users. So the challenge in the full duplex is when the base station transmitting at the high power to the downlink user, it will cause self-interference to the receiving antennas. So this self-interference is very severe. Because of this self-interference, so far there's no full duplex system is implemented in the real scenarios. So we are going to cancel this self-interference. Dr. Abhijit will be explain to you how we did this cancellation in a minute. So this self-interference that we need to cancel is around 110 dB that we need to cancel to demonstrate this full duplex concept. We implemented here 802.11 AB scenario with 2.45. The operating frequency is 2.45 gigahertz with the bandwidth of 5 megahertz. We will be able to show bigger bandwidth as well, but in this demo we will be showing only 5 megahertz bandwidth.
So basically this interference cancellation is done in two ways. First is the analog cancellation, and the second one is the digital cancellation. So basically what we did here, in analog, first we take a signal from the transmitter and put it into the power divider. So this power divider divide the signal into two parts. First signal goes to the transmitter, which transmit the signal to the downlink users, and another goes to the receiver side of the same base station, and it is connected with wires and some attenuators here. So we choose the value of attenuator and the length of the wire, so that the signal which is coming at the receiving side of the base station from two paths, one is from over the air and another is from the wire, they have 180 degree phase shift, so that it cancels the signal. And after that we have some self-interference that exists after analog cancellation. This can be cancelled by the digital cancellation. So in digital cancellation, first we estimate the channel and use this channel to cancel the remaining self-interference. So this is the power spectral density of noise at 5 MHz bandwidth and 2.45 GHz carrier frequency. the blue one represents the power spectral density of the signal after analog cancellation, and the red one is the power spectral density of signal after analog plus digital cancellation. This constellation shows the QPSK constellation, which is transmitted by the uplink user. QPSK modulation is used for the weak user, and the BPSK modulation is used for the strong user. This figure shows the received constellation for the weak user in the presence of interference, which is created by the uplink user. Similarly, this figure shows the received constellation for the strong user in the presence of interference, which is again created by the uplink user. So as the weak user has a QPSK modulated data, and the received constellation is also a QPSK, and hence it decodes its own data very easily. So the bit error rate is 0 for the weak user. Similarly, in the case of strong user, so first it decodes the weak user data and then perform successive interference cancellation, and then decode its own data. So it is observed that from this figure that it is a EPSK model data, and hence the bit error is 0 here.
I'd like to thank our funders, EPSRC for our Mango project with University of Edinburgh and Manchester, and UKIERI project with NIT Trichy and IIT Indore.